So here we're going to look at some buffer calculations. Okay, so the first question that we have says, a buffer solution contains ethanoic acid, which has a pKa of 4.76 at a concentration of 1 mole per decimeter cube, and sodium ethanoate. If the pH of the buffer solution is 4.20, what is the concentration of the sodium ethanoate? So over here again we have an acidic buffer solution, right? A pH of 4.2, and what we have is we have ethanoic acid, right? And we have a salt of its conjugate base. So we have sodium ethanoate. And we know that the conjugate base ionizes completely. To form ethanoate ions, right? And they've also given us the pKa here. And we know that the Ka for ethanoic acid, right? The Ka for ethanoic acid is the concentration of H plus times the concentration of CH3CO2 minus divided by the concentration of ethanoic acid. Now, for a buffer solution, right, we can assume that the acid remains unionized because a very small percentage of the acid ionizes. We can take this concentration of acid, right? We can assume that this concentration is the initial concentration of acid that we used. And because we have a salt of the conjugate base, we can assume that all the conjugate base comes from the salt, right? We can assume that all the conjugate base comes from the salt, right? Now, they've given us the pKa, right? So we can calculate Ka. We know that the Ka is equal to 10 to the power of negative pKa, right? They've given us the pH, so we can calculate the H plus concentration, right? So here Ka is 10 to the power of negative 4.76, and we know that the concentration of H plus is simply 10 to the power of negative pH, which is 10 to the power of negative 4.20, right? And they've also given us the initial concentration of acid, which is 1 mole per decimeter cube. And they want us to find the concentration of sodium ethanoate. So let's say our concentration of sodium ethanoate is x moles per dm cube, and we're assuming that all the conjugate base is coming from the salt, right? So if the concentration of the salt is x, we know that the concentration of the conjugate base is also x moles per decimeter cube, right? So this concentration here is just x, right? So we can calculate the concentration of the salt, right? That's just x. That's what we want to find. You know the Ka over here is 10 to the power of negative 4.76. The concentration of H plus is 10 to the power of negative 4.20 times the concentration of the conjugate base. That's what we want to find, right? The salt concentration divided by the initial concentration of acid, which is 1 mole per decimeter cube. And that gives us the concentration as 0.275 moles per decimeter cube. So that's our answer. The next question that we have here says 100 cm cube of 0.0515 moles per dm cube nitrous acid were mixed with 50 cm cube of 0.0428 moles per decimeter cube sodium hydroxide, right? They've given us the Ka, the acid dissociation constant for nitrous acid. Calculate the pH of this buffer solution. So over here again we have nitrous acid, that's HNO2, reacting with sodium hydroxide to form NaNO2, right, and H2O. Is a neutralization reaction, and they've given us the concentration and the volume of the acid and hydroxide alkali used over here. You know the number of moles of HNO2 is concentration times volume. Concentration is 0.0515. The volume is 0.1 decimeter cube. So therefore the number of moles is 0.00515 moles, right? Similarly for sodium hydroxide, we know the concentration is 0.0428, the volume is 0.05 decimeter cube, right? That's 50 cm cube. The number of moles comes out to 0.00214 moles. So over here we can clearly see that sodium hydroxide is limiting, right? The acid is in excess. So after the reaction is complete, what we have is, we have all the sodium hydroxide reacts, right? All the sodium hydroxide reacts. And obviously for every 1 mole of this, we need 1 mole of acid to react. So the acid is in excess, right? So after the reaction, this is how much acid we have left over, right? 0.00301 moles. And obviously we have all the sodium hydroxide is reacted. And of course, we know that we've made this many moles, 0.00214 moles of NaNO2, right? Because right, it's for every mole of NaOH and HNO2 that react, 1 mole of NaNO2 is produced. So we can say over here that we produced 0.00214 moles of NaNO2, right? So again, we've ended up making a buffer solution. We have a solution of a weak acid and its conjugate base, right? Because we've made a salt of the conjugate base. So we have the following equilibrium for this buffer, right? We have HNO2, right, forming NO2 minus ions and H plus ions, right? The Ka for this is 7.20 into 10 to the power of negative 4 moles per decimeter cube, right? They've given that to us. And we also know that for this buffer solution, right, we know that since we formed NaNO2 here, we know that that will ionize completely in solution, right? These are just free aqueous ions, because salts, right? This is a completely soluble salt. So this ionizes completely in solution to form Na plus and NO2 minus, right? So we can say that in this equilibrium, we can assume that the concentration of NO2 minus ions is, or the total number of moles of NO2 minus ions is just 0.00214, right? We can assume that all the NO2 minus ions come from the salt, right? So we can assume that this concentration, right, or this number of moles is the same as this, right? So again, in this buffer solution, we have 0.00214 moles of NO2 minus ions, right? That is from the salt. And we have how many moles of HNO2? We can assume that the final concentration of acid at equilibrium is the same as the concentration here, right? We can assume that it's unionized. So we have 0.00301 moles of acid. Again, over here, right, what we had was, we had a weak acid that we reacted with NaOH. We had excess acid, and we ended up making NaNO2, and we had acid left over. Now this NaNO2 is it's completely ionized in aqueous solution, which means that now we have a large amount of conjugate base, that's NO2 minus ions, coming from the salt. Okay, so we can assume that all the NO2 minus ions are coming from the salt that we produce here, okay, from this reaction, rather than from the acid itself. Okay, so we can assume that this concentration, or this number of moles, is just the same number of moles as we have of NaNO2 here, right, or however much NO2 minus ions are produced in this reaction. And we can assume that the weak acid remains unionized, right, in this buffer. So we need to find the pH of this buffer solution, right? We need to find the pH of this buffer solution. We know the Ka. The Ka is simply the concentration of H plus ions times the concentration of NO2 minus ions divided by the concentration of HNO2. Now over here we know that the Ka is 7.20 into 10 to the power of negative 4 moles per decimeter cube. The concentration of H plus we want to find, since we want to find the pH. The concentration of NO2 minus right, is just the number of moles. Remember, the concentration is just the number of moles per unit volume, right? So we have 0.00214 moles of NO2 minus ions. So that's number of moles, 0.00214 divided by volume, which is 150 centimeter cube. That's 0.15 decimeter cube, right? And we have the same thing for the concentration of, we're going to find the concentration of HNO2 in a similar way, right? We know that the concentration of HNO2 is again the number of moles per unit volume. We have the same volume, same solution, right? We have 0.00301 divided by 0.15, right? Now here again the volumes will just cancel. So the idea is for buffer solutions, right, the molar ratio between the conjugate base and the acid is the same as the concentration ratio, because it's the same solution, right? You divide number of moles by volume, it's the same volume in both numerator and denominator, so the volume just cancels out, okay? So over here, if we calculate the concentration of H plus ions, it comes out to 1.01 into 10 to the power of negative 3 moles per decimeter cube, which gives us a pH of minus log of H plus, right? That's 2.99. Now, one thing to notice here is that ultimately the pH of a buffer solution simply depends on the ratio between the molar ratio between the conjugate base and the acid, right? So for example, if here I could use double the concentration of conjugate base and I could have double the concentration of acid. As long as the ratio between them is the same, the pH will be the same for that buffer solution. So the pH of a buffer, okay, the pH of a buffer simply depends on ratio, right, between concentration of conjugate base and concentration of acid, okay? And here again the molar ratio is equal to the concentration ratio, right? Because you have the same volume, you have the exact same solution. If you just divide number of moles by volume, right, in both cases the volume will just cancel out. So ultimately you're just taking the molar ratio between the two, and the ratio of the moles of conjugate base and acid determines the pH of a given buffer. The next question that we have says, calculate the mass of sodium propanoate that must be dissolved in 1 decimeter cube of 1 mole per decimeter cube propanoic acid to give a buffer solution with a pH of 4.5. So over here we have the following equilibrium, right? We have propanoic acid, right? That's our weak acid here. We have a buffer solution, right? And these propanoate ions are coming from the salt, right? Our salt here is sodium propanoate, right? Now we don't know what mass of sodium propanoate we've used to make this. We don't know what mass of sodium propanoate we've used to make this buffer solution, right? What we do know is the pKa. They've given that to us, right? The Ka is obviously just 10 to the power of negative pKa, right? Ka is 10 to the power of negative pKa. So we know that the Ka over here is 10 to the power of negative 4.87, right? And we also know over here what the pH is, so we can calculate the concentration of H plus ions. Concentration of H plus ions is simply 10 to the power of negative pH, that is 10 to the power of negative 4.5, right? Again, the reason we're doing that here is because we just want to substitute these values into the Ka expression, right? We know that the Ka for this buffer solution is the concentration of the conjugate base times the concentration of H plus divided by the concentration of acid, right? Now again, the conjugate base is coming entirely from the salt, We don't know the concentration of the base. We have found the Ka, that is 10 to the power of negative 4.87. We want to find the concentration of the base and therefore the salt. We know the concentration of H plus ions is 10 to the power of negative 4.5. And the concentration of acid is just 1 mole per decimeter cube, right? We assume that the final concentration is just the initial concentration. So this is just 1 mole per dm cube, so we just divide by 1, right? Which is just we don't need to do that. So then, what does the value of X come out to? X comes out to 0.4265 moles per decimeter cube, right? So we know the concentration of propanoate ions. We know the concentration of propanoate ions in this buffer solution. Now we know that the propanoate ions came from the salt, right? So we have CH3, CH2, CO2, Na. That ionized completely to form CH3, CH2, CO2 minus and Na plus, right? And we know the concentration of this, right? We know that we have 0.4265 moles per decimeter cube of propanoate ions, which means that the number of moles is just the concentration times the volume. The volume of the solution is just 1 decimeter cube. So the number of moles is just the concentration, which is 0.4265 moles. Right, so we have 0.4265 moles of this propanoate ion in solution, which means that we use 0.4265 moles of this salt, right? Because for every mole of salt, you get 1 mole of the conjugate base. So now we know the number of moles of the salt, right? We know the number of moles of the salt, and we know that the mass is equal to the number of moles times the molar mass. The number of moles is 0.4265, and the molar mass is 96.07. So this comes out to 41.0 grams. The next question that we have here says, an acidic buffer is formed by mixing 0.124 moles of ethanoic acid with X moles of sodium hydroxide in 1 decimeter cube of solution. The pH of the buffer formed is 4.81. Given us the Ka for ethanoic acid, right, at 25 degrees Celsius, calculate X. So over here, of course, we're reacting ethanoic acid with sodium hydroxide, right, and we're forming sodium ethanoate and water, right? It's a neutralization reaction, and over here we're forming a buffer solution, right? The pH of the buffer formed is 4.81. So we know that we're forming an acidic buffer, which means that ethanoic acid is in excess, because in order to form a buffer solution, we need a mixture of the weak acid and its conjugate base. So we know that all the NaOH will react and acid will be left over, and we'll also have a salt of the conjugate base produced, and therefore a buffer solution produced. Now we know that we have 0.124 moles of acid and we have X moles of NaOH. That's what we have to find, how many moles of NaOH we have. And we know, as we just said, that we know that the acid is in excess, so we know that all the sodium hydroxide reacts, right? So we know that X moles of sodium hydroxide react, and therefore X moles of acid react, right? Because they react in a 1:1 ratio. So after the reaction is complete, we have 0.124 minus X moles of ethanoic acid. We have 0 moles of sodium hydroxide, and we've also formed X moles of the salt of the conjugate base, right? So what that means is that now we have a buffer solution, right? We have an acid, we have a solution of an acid and its conjugate base. So this is the buffer solution that we have, right? We have this buffer now, right? And again, we know that this is coming from the salt, right? That is, right, the conjugate base is coming from here. right, from the salt that was produced. And obviously the acid, the amount of acid that we have is just the amount of acid that was left over after the first reaction, right? We assume that none of it ionizes. So we know that we have 0.124 minus x moles of acid, and we have x moles of the conjugate base. So now that we have the number of moles of each of these species present, right, in this buffer solution, we can find the value of x, right? We know over here that the Ka is equal to the concentration of H plus times the concentration of the conjugate base divided by the concentration of the acid, right? And again, the conjugate base is just coming from the salt, right? We know how many moles we have of conjugate base, and we know how many moles we have of acid, right? Now, remember, because it's just a buffer solution, right, both of these species are present in the same solution. So we've already learned that the molar ratio will be the same as the ratio of their concentrations, right? So we actually don't need to find the concentrations here. We can just plug in the moles, okay, into this expression. And here in this case, the concentration will actually be the same as the number of moles, because the concentration is just number of moles per unit volume, and the volume is just 1, right? So we know that the Ka, which is 1.74 into 10 to the power of negative 5 is equal to the concentration of H plus, which is 10 to the power of negative 4.81. Remember, concentration of H plus is just 10 to the power of negative pH, right? Times, we have the number of moles of the conjugate base, that's X, divided by the number of moles of acid, which is 0.124 minus X. I'll repeat, the ratio of the moles will be the same as the concentration ratio. So it doesn't matter if you take concentration here or number of moles, right? Because they're both in the same solution. So if you divide this number of moles by V and this number of moles by V, whatever the volume of the solution, the volumes will just cancel out. So now if we divide 10 to the power of negative 4.81 on both sides, we get 1.123, right? And then we multiply 0.124 minus X on both sides, so we get 0.124 minus X is equal to X, right? And if we solve for X, X comes out to 0.0656 moles, okay? 0.0656 moles. So that's the number of moles of NaOH that was used initially to make this buffer solution.